Hello, ladies and gentlemen. This is Mr. Hunter, and this is your Energy Notes. So, energy is the ability to do work or make change. And so, in everything that we do, we use energy. And so, energy is how we apply forces over a certain amount of distance and how we make change, how we make things go faster or slower. It all results in the form of energy. So, the unit for energy is joules, Joules, as you see the notes here. And just like the Newton, the joule is a derived unit, which derived means it's made up of basic other units. So for example, as we're going to learn about, gravitational potential energy is mass times gravity times height. So if you look, mass is kilograms, height is in one of the meters, and then times acceleration, which is meters per second squared. So when you multiply all of that out, the basic units are really kilograms times meters per second squared. So that comes out to kilograms times meters squared over second squared. It is definitely worth noting because joules can make up different types of units. You're also going to see another derived unit come up for energy when we get to the work equation. Okay, so in terms of energy, in physics, we deal with three basic types of energy. The first energy that we really deal with is called kinetic energy. The definition of kinetic energy is the energy an object has as a result of how fast the object is moving. So kinetic energy only depends on its speed and nothing else. Well, its speed and its mass, but typically the mass of an object is not changing when you're doing an experiment or trying to measure its kinetic energy, unless you're in a car crash. But it's the energy of an object has as a result of how fast the object is moving and only its speed. So if you like have an object moving and it's traveling down this ramp, well, it still has gravitational potential energy, but as its speed increases, so does its kinetic energy. So the equation for kinetic energy is 1/2 times mass times velocity squared, or I have it written here as mv squared over 2. So ke equals mv squared over 2. So you take the square of your velocity, you multiply your mass, and divide it by 2, and that's how much kinetic energy you have. Once again, it's energy, so the unit for energy is joules, mass is measured in kilograms, and velocity is meters per second. And check this out, just like in the beginning where I showed you that a joule equals a kilogram times meters squared over second squared. Well, let's plug that all into the KE equation. Mass is measured in kilograms, and velocity is meters per second, but it's all squared. So what does that turn into? It turns into kilograms times meters squared over second squared. So it turns into the exact same thing that I was talking about with gravitational potential energy, as well as the units I'm showing at the top. So the next energy that we have is what we just talked about, gravitational potential energy. And this is the energy that you have as a result of your position. The reason why we say position and not necessarily height off the ground is if I have a pendulum swinging back and forth, its position is relative to the lowest part of the pendulum. That would be its change in height, quote unquote, because that pendulum is never going to hit the floor. It's only going to swing to the bottom of its swing. So at the bottom of its swing, it has the most kinetic energy, and when it gets to the top of the swing, it has the most gravitational potential energy because it has the most change in position. So we define it as the energy an object has as a result of how far it is above the surface. Or like I said in the pendulum, how far it's above its lowest point. So the equation for GPE is mass times gravity times change in height. Um, because if you think about gravitational potential energy, usually it's I'm 5 feet off the ground. How much energy do I have? Well, if it's gonna 5 feet, I mean 5 meters. We're 5 meters off the ground, it's gonna change to 0. Then I can figure out my GPE. In the same token, I could say, hey, how much energy is left after it falls 3 meters? Well, my change in height would be 5 meters, and then it would change to 2 meters. So I could do 5 minus 2, which is 3, and plug that in, and I can get my delta PE, which is kind of the equation that your reference table uses. And also, A of g is the acceleration due to gravity. On your reference table, it uses g, just so you can delineate between the two. Remember, g is always 9.8 meters per second squared. And just as I taught before, x's and y's are like oil and water. So g is always available on the y-axis. It's never available on the x-axis because it's the x-axis, and we don't use x-axis variables on the y and vice versa. So the last energy that we have to deal with is spring potential energy. This is the amount of energy stored into a spring as a result of how much it's stretched or compressed. Now, once again, it's energy, and it looks very similar to the kinetic energy equation, very similar in the fact that it has the same format. So spring potential energy equals 1/2 kx squared, or kx squared divided by 2. Now, k is the spring constant, and its unit is newtons per meter. So spring potential energy is still in joules, and the spring constant is a unit, it's newtons per meter. I say it as how strong the spring is, because your shocks in your car are springs. That's exactly what they are, but they have a huge K value. Like if you could actually get to one of those, like even you standing on it won't compress it. So strong, so how strong the spring is. So how strong the spring is. And the variable x, which is measured in meters, is the elongation or compression of the string, which essentially means how much does it stretch or how much does it compress. Now, typically, most problems say, hey, what's the spring potential energy? And they say, hey, I pull the spring with a certain amount of force, and here's my distance, and sometimes they don't give you a K. Excuse me. So in this case, we use something called Hooke's law. And this guy Hooke basically demonstrated that the force of the spring is directly proportional to the spring constant and how far this spring stretches or compresses. So sometimes, and I can easily find this, if I hang a mass off the spring, so like here I draw a little stand, and here's my spring, and then I hang a mass off the end, and I can actually measure the x. I know this mass, let's say it's 5 kilograms, so I can actually, in some cases, the force of gravity, in this case in particular, will equal the force due to spring, which equals kx. Since I can measure and know this, and since I can measure an x, I can solve for k. Because if I solve this equation for k, it's force divided by x, which is newtons divided by meters. So Hooke's law is really important in figuring out the K value when you don't have it. Especially you'll be doing that in your conservation of energy lab, because you guys will be, most of you will be using a spring, and because you're using that spring, you're going to have to figure out its K so you can figure out the spring potential energy. Now, work and power. Definition of work. Energy used or made by applying a force over a certain distance. Here's the critical part, ladies and gentlemen. The force has to be in the direction of the distance. For example, if I'm lifting a book, I'm lifting against the force due to gravity. But if I'm carrying a book across the room, the distance, the direction of my distance, which would be straight forward or on the x-plane, is not in the same direction of my force, which would be on the y-plane. So therefore, according to physics, I'm doing 0 joules of work when I carry something. However, that's not the case if I were to push that book across the table, because the force of my push is in the direction of the distance, so it would be doing work. So the equation for work is force times distance, and you guys use this in Power of the People lab when you ran up and down the stairs, because the force that you were working at against was the force due to gravity, so you multiplied your mass times acceleration due to gravity and multiplied it by the distance, or in this case, the height of the stairs, to find your work. I also made you equate that to gravitational potential energy, because when you break down that equation, they actually turn out to be the exact same equation, so therefore, running up the stairs, you do the same work as as much as you do in terms of gaining gravitational potential energy. So the unit for work is joules. And another unit for joules is newtons times meter. Because if you think about it, Newton is kilograms times meters per second squared times distance. Oh, look, if I actually break down the newtons, I get kilograms times meters per second squared multiplied once again by meters, which gives me kilograms times meters squared over seconds squared, which is a newton times a meter. So that's another unit for joules. Now, power is how much work you do in a certain time period, or force times the average velocity. So the equation for power is power equals work over the time, and the unit is watts or joules per second. So power is work over time. And if you think about it, well, what does work equal? Work is force times distance divided by time. And if you look at this equation, that looks really, really familiar because distance over time is average velocity. So the unit for power is joules per second, or we simply call it watt. And if I really wanted to, I could say newtons times meters per second, which is its own crazy type of unit if I were to carry that out, which I'm not going to because I've never seen the Regents do it. Doesn't mean they won't. They could potentially ask you that question. So the last part of what I need to show you, and we'll be done with energy, is conservation of energy. Energy cannot be created or destroyed. It can only change forms. This means that the total energy of the system is the same. So as long as I'm not doing work on the system, aka putting energy into the system, the total energy doesn't change. And like I said here, the only way to add energy is to do work on the system, or subtract energy, aka doing work on the system through friction, which leads us to total energy, mechanical energy. And this is kind of the crux of this whole unit, because your total energy is the sum of all of your energies, a sum of all your kinetic energies plus your gravitational potential energy plus your spring potential energy plus your Q, which is internal energy, which is kind of like thermal or other forms of energy where we can't really get it back. So this includes friction. It also includes the part deforming. So like when I drop a ball, friction and part deformation. Good word, deformation. Anyways, so from the part deforming or friction, we lose energy, and it just changes forms. We never lose that total energy. It just kind of changes into a form we can't easily get back. So I just want to note that internal energy and kinetic energy are like mortal enemies. They're like the Jedi and the Sith. They just do not like each other. And Q always steals energy from kinetic energy. Think about it. This is what happens when our cars driving down the street. I'm not even hitting the gas pedal, and I eventually slowed to a stop. Why? Because friction. Because friction between the tires and the road, and friction in my engine eventually brings my car to a stop. So that internal energy ate my kinetic energy. Now, mechanical energy is just the sum of your kinetic and potential energies. It's like, here's the perfect energy in a system if we didn't lose any of it to Q. So that is energy in a nutshell. I encourage you to definitely review and write down those notes, and come talk to me if you have any questions. I'm out.